Hello students, let's go for the experiment on measurement. Okay, let's do it. Let me share the screen. Um, and we are right here on measurement. And we relate this experiment on the significant figures. Okay, great. Let's do it. Um, let's start with this. Okay, measurement again. This analysis is, we're not doing measurements like a real measurements in the lab, but we are actually working with the measurement with data with precision and accuracy using significant figures. Okay, let's do it. From the beginning, when we're dealing with exact values, right? Values that we use when we count object, for example, or when we do comparison, 1 hour is equals to 60 minutes, it's not the same as when we're doing measurements in the lab, right? When we're doing measurements in the lab, we're dealing with averages, right? Not with exact values, correct? That involves in the measurement. In this, again, experiment, let's go for measurements that are expressed in terms of its accuracy or its precision. Correct. Let's define accuracy. Accuracy of a measurement refers to a number of digits, right? Called significant digits or significant figures, which indicate the number of units that we are sure, right, of having counted when making a measurement. The greater the number of significant figures given in a measurement, the better is the accuracy and vice versa. Okay, and these figures is also given by the precision, right? The numbers of digit, you use a ruler, you use a micrometer, right? It's different precision, different significant figures. So it depends on the device you're using in the lab. So if we were using the same device all the time, right, we have no problem in reporting our measurements. The problem is when we use different devices with different units and we're adding or multiplying quantities, right, using those devices. The point is with which precision we are supposed to report our answer. With the precision of the ruler or the precision of the micrometer, for example. To do that, we have some rules. The rules are now given in this experiment, right? The rules will help us to represent the answer of our measurement, correct? Once we are working with different devices with different precision. Okay, with which precision, again, we are supposed to report the answer at the end. Okay, let's do it. Let's go for significant figures or digits. We have some rules. Right here, when we're dealing with significant figures, the main point are the zeros, right? The zeros are causing all these rules, right? Because if we don't have zeros, everything is correct. But when zeros are present, we have to create rules to represent, right, the measurement, like in this case. We have these rules. The first one, all non-zero digits are significant. Again, if we have no zeros, everything is perfect for significant figures. Like in this example, this measurement has 4 significant figures. For simplicity, significant figures, we use SF, right? Okay, rule 2, all zeros between significant figures are significant, right? All zeros between significant figures are significant. Like in this case, right, we have 5 significant figures. The next one, in a number greater than 1, a zero that is especially tagged, such as a bar, is significant figure. Or like in this case, we have zeros, again, and one of them is tagged, means that that is significant. In this case, we have 3 significant figures. If this is not tagged, of course, it's not significant. All zeros to the right of a significant figure and decimal points are significant, like in this case, correct? 6.20 centimeters has 3 significant figures. A whole number measurement zeros at the right that are not tagged are not significant. So again, like in this case, these 2 zeros are not tagged, right? So they are not significant. In this case, we have for this quantity 2 significant figures. And finally, in a measurement of less than 1, zeros at the left are not significant, correct? Like in this case, we have 0.00671 kilograms has 3 significant figures. Great. Now let's go for measurements. Imagine that we're doing this measurement. We have this object, this cylinder, correct? And we are using a ruler with centimeters, correct? So let's estimate up to do this measurement. For sure, we know that is in between 7 and 8, correct? And for sure, we know that is more than 7 centimeters long. So this is for sure. Now, the next digit, we have to guess it. Imagine that we guess it to 7. So it's gonna be 7.7. These two numbers, that one that for sure we know is correct, and the guess one are called significant figures. These are the significant figures, like in this case, right? The length for this object is 7.7 centimeters. And it has 2 significant figures. Let's again use the same object, but now let's change the device. In this case, we have a ruler with millimeters. So we increase the precision. Again, in this case, we know it is 7, but also we know that this object is passing this line 7 millimeters. So, but now the edge of the end of this object is between 7 and 8 millimeters. So we have to guess again the last digit. And what do we have? We have that in this case for sure is 7.7, but we have to guess the last one, 5. These 3 again form the significant figures or significant digits. And it's gonna be 3 significant figures, correct? Okay, perfect. Remember, the last one is the guess one, the guess value. Great. Let's do another example using significant imprecision now. Imagine that we have to hit this target with balls, right? And the balls are hitting very close, right, to the target, and sometimes hitting the target. And in this case, what do we have? Well, this is the case when we have high accuracy and low precision. Let's go to another example. It's the same target, but now look, the balls are hitting right that spot, but far away from the target. This is the target right here. So it has a high precision, look, but low accuracy. Perfect. Now let's go for the next example. Now let's do examples using measurements. Let's apply the rules for significant figures. Okay, let's do it. Imagine that we have this quantity. Remember, all digits different from 0 are significant. Correct, right here. Remember, all zeros between significant figures are significant. So how many significant figures? 4. The next one, 0 that are not tagged are not significant. Like in this case, we have 3 significant figures. This one, 0 is tagged, right, is significant. So how many significant figures? 3. Okay, so 1, 2, 3, perfect. The next one, we have zeros, but none of them is tagged. So those are not significant. So how many significant figures do we have? 2 significant figures. Okay, the next one, the same thing, right? How many significant figures do we have? 3 significant figures. The next one, oh, now let's go to precision. Yes, let's go to precision. In this case, let's define precision. Precision of a measurement refers to the smallest unit with which a measurement is made. It's like a decimal point, okay? That is the position of the least significant figures. Let's say how many significant points. If we increase the decimal point, right, in the measurement, we increase the precision. For example, we have this measurement, we have precision, and we have significant figures. Let's see the difference. Again, let's look for precision. The precision is, according to this definition, the position of the last significant figures. What is the last significant figures? Right here in the units, right? We are in the unit. It's gonna be 1 foot. And how many significant figures? 4. The next one, again, the precision is the last significant figures is the last the position of the last significant figure, which is 1. Well, it's gonna be 1 meter. How many significant figures? 4. Okay, the next one. Remember, right here, what is this? These are not significant, correct? What is the significant figure? Is this one in the hundreds, right here in the hundred. This is unit, tens, and hundreds, right? So we are right here. So it's gonna be 100 meters. And remember, these are not significant, so we have 2 significant figures. All right. Now let's do for precision for this one. Again, this is significant, so it's gonna be in the order of the hundreds, right? It's gonna be 100 kilometers. And what is the precision? Significant figures 3. This precision 100 kilometers, and this is significant figures 3. One more. Again, what is the last significant figure? It's gonna be this 0, right? The units for this one, let's say. This 0 are the for the precision is gonna be 0.0001 meters. And how many significant figures? 4. Okay, great. Let's go for the next one. Again, this is gonna be the precision. So it's gonna be 0.01 times 10 to the 4, right? The square meters. Or if we multiply, we can get 100 square meters. The precision, significant figures, so we have 3. Okay, yeah, that's the way how we work with precision and significant figures. Perfect. Now let's go to add and subtract and multiply and divide. Again, when we're dealing with quantities and we are adding actual measurement, we're adding, right, and subtracting, we make a group. We have another group. The other group is when we multiply or divide measurement. Okay, let's go for this one. The rules for add and subtract. The first one, all the terms must be with the same unit, correct? If they have different units, we have to make all of them with the same units. Okay, and then add or subtract. And finally, right, round the result to the same precision as the least precise measurement. Okay, we have an example. We have this measurement. Okay, now it's a sum. Let's add this for a measurement. And what do we have? Well, we have this quantity. This is correct, okay? This one is correct, but that's not the correct way how we represent the answer. Remember, right here, we are looking for the best way to represent the answer when we have different devices doing the measurement. We have different precision, means we have different devices. Now, the point is, with which precision we are supposed to report the answer. The answer, according to this rule, when we are dealing with addition and subtraction, is the precision. We are using the precision of the least precise measurement. Okay, now let's find precision for each measurement. What is the precision for the first one? 0.1 miles. For the second one, 1 mile. For the third one, 0.01 mile. For the last one, 0.001 mile. Okay, what is the least precise? 1 mile. So this answer must be represented with only this precision, right? In this case, it's gonna be 144 miles. Correct? Perfect. Let's go for another example. We have this, again, measurement, and this is an addition. And let's find the sum. Again, this is correct. It's correct, but it's not the right way to represent the answer. Again, we have to use The rule for adding and subtracting means that the result must be to the same precision as the least precise measurement. Then let's look for precision. And these are the precisions for this measurement. What is the least precise? The first one, right? The first one is the least precise with 1 decimal. Okay, means that this answer must be only with 1 decimal, right? Perfect. And what do we have? In this case, gonna be 638.2 meters, right? We rounded with this precision. Now let's go for a subtraction. Okay, what do we have right here? We're subtracting grams minus this amount of kilograms. Again, we need to convert up these terms or measurement with the same units when we are adding and subtracting. Imagine that we want to convert kilograms into grams, correct? So right here, look, what is the precision? It goes to this decimal. Actually, this 0 right here is accurate, is part of the accuracy, right? See how many significant figures do we have? 3, right? So this 0 is significant. When we do the conversion, this 0 also must be significant right here, correct? Perfect. Now let's subtract these two measurement, correct? And what do we have? Well, we have this answer, correct? The answer is correct. But now let's apply precision. What is the precision for this measurement? 0.1. For the second one, it's gonna be 10 meters. What is the least precise? 10 meters. So what should be the answer for this result? It's gonna be 660 grams. Right, because that's the precision right here in the tenths. Okay, perfect. Now let's go to multiply and divide measurement. It's another group. In this case, we have, again, the first rule, the first one, multiply or divide the measurement as given. In this case, don't worry about they have the same units or not, okay, in general. And then round the result to the same number of significant figures as the measurement with the least number of significant figures. Okay, perfect. In this case, we're dealing with significant figures. When we add and multiply, we're dealing with precision. Okay, great. We have this product we're multiplying, right? We multiply these 3 measurements, and this is the answer, and the answer is correct. But that's not the right way to represent the answer. We have to round this result to the same significant figures as the measurement with the least number of significant figures. For example, how many significant figures do we have? 3. How many? 3. Right. How many for the other one? 2. So what is the has the least number of significant figures? Right. It's gonna be 2, right? 2 has the least number of significant figures, so that's gonna be 2.1, in this case, cubic meters. Okay, that's the least one. Perfect. Another example. Now let's divide. The multiply and divide, right? This time is divided by this amount, and this is the answer. The answer is correct, right? You check the book when you're looking for answers when you have homework problems, right? The answer is not given in this way. The answer is given with 2 or 3 significant figures. And that depends on this analysis, correct? For example, right here, let's look for significant figures. 4 significant figures, 3 significant figures, 3. What is the least one? 3. So it's gonna be in this way equals to 61.8 meters. We have another one. In this case, look, when we divide a measurement by a number, but this number is not a measurement. We don't apply the rules when we're dealing, multiplying or subtracting by a number. This goes in this way, correct? That's on for significant figures, and right here is no units, no measurement. Okay, now let's make a combo of addition, right, and multiplication. Again, perform all the operations inside parentheses first, right? Evaluate all powers, and perform any multiplication or division in order from left to right. Then express each product or quotient using its correct accuracy. And finally, perform any addition or subtraction in order from left to right. Then express the final result using the correct precision. Okay, perfect. Let's do this example. We are multiplying these two measurements. Now let's add this measurement square and add these two measurements and divisions. Okay, perfect. Let's do it. When we multiply these two, we get 63.25. When we make the square of this measurement, it's gonna be this answer. When we do this last term, we get that answer. Okay, now let's apply the rules for multiplying, right? Let's find the significant figures. This one has 3 significant figures. This one has 4. This one has 3. This one has 3. And the other one has 4. Okay, for the result of this product, right? Let's apply the rule. How many digits we're supposed to have, right? You have to round, remember, to this accurate, like over here, right? This accurate number. Okay, from here we get that this quantity goes to 6.3 because we rounded to the number with the least significant figures. In this case, is 3. The next one, 3. Let's round it also to 3. Correct. So it's gonna be 448. Okay, and then this one also to 3. Okay, let's do it. Let's round it to 3 significant figures. Now, let's add these 3 right measurement. Correct. And to add these 3 measurements, we use precision. Remember? Okay, let's find the precision. Well, this is the answer, correct? This is the answer, and this is correct. But we have to use precision to represent the result. Again, use precision. What is the precision? It's gonna be 0.1. What is the precision for the next one? It's gonna be 1, and the other one is gonna be 1. So in this case, remember, we represent the answer with the least precise, when we're adding and subtracting, with the least precise value. In this case, it's gonna be 1. So the answer is gonna be 879 square meters. Okay, perfect. So with this, we have all the information to do our experiment. In our experiment today, let's work with significant figures. So we have this set of measurement. Please calculate the result. Please give me the result when you do it, and then apply the rules. As before, look, as right here. We have the result, right? This is the result, and then I apply the rule. The same thing right here. Please go and find the answer without rules, and then apply the rules to find the answer that's supposed to report. For the next one, find the answer without rules, and then give me the answer, the right answer that we're supposed to report this measurement. Okay, please. And it's gonna be today's experiment. Give me the values right here, apply the rules, upload it right through Canvas, and I'm gonna grade it, right? And this is again today's experiment. Okay, great. Let me stop the share. Okay, and see you in the next experiment. Bye. Let me end this video. Again, upload this on Canvas, post it on Canvas in time. You can take a picture of your work. Also, please don't forget the title, don't forget the purpose, don't forget the calculation and the conclusion, please. For example, when we're dealing with the purpose is usually related to the title of the experiment. For example, what is the title measurement? And what else? We have precision and accuracy or significant figures. So a good purpose should be representing measurements by precision and accuracy or significant figures. right? Or another purpose should be using significant figures, right, to represent the result of measurement. Okay, great. See you in the next video.